my name is Han Wu. I'm currently an associate professor at the Peking University. So today I'm going to share with you some of the latest progress we have on the flip technology, which is the flip 3D. So today the presentation title is flip 3D, a novel 3D integration technology with dual-sided integration capabilities. So for my today's presentation, I'm going to give a brief introduction, and then I will talk about the process flow, followed by the ultra-scaled design and the PPA, and then I will talk about some of the new concepts of the interconnects, which features dual-side interconnections. And then I will talk about some of the system integration we have enabled by the flip 3D integration. And in the end, I will make a conclusion. So now let's get started. So, for futures AI system, we all know that the system requires a lot of computation power, which in other words requires a lot of transistors to be packed in the system. And to pack more transistors, actually there are two ways. The first way is the advanced logic. So basically we scale down the transistor and we have more advanced technology node from the 10 nanometer to 7 to 5 to 3 or 2 or to even beyond 1 nanometers. So this is for the advanced logic. And the other part, which actually is the advanced packaging. So the industry is evolving from the 2D packaging to 2.5D and 3D, and also the M3D integration to pack more transistor. And by combining the advanced packaging with the advanced logic, actually, the industry already have the solution to have a transistor then integration number beyond 1 trillion transistor, which is already released by TSMC in their technology symposium. However, as the industry have already get the solution for the academia, we need to think about something more aggressive or more advanced, and then come up with the question: how about the way to achieve 1 quadrillion transistors, which is 15 zeros after the 1? So there's a lot of transistors, and we really need to think about how can we realize this. So today I'm going to share some of the thoughts we have from Peking University regarding to this solution. So let's first talk about the logic in terms of the logic scaling for the advanced logic. Actually, there are two clear trends. The first one is the advanced transistor. So basically, we are evolving from the planar to the FinFET to GAA and to the stack transistor or CFET. So you can see the advanced transistor part, we are moving towards the 3D transistor stacking. And the other part actually is the interconnects. We are evolving from the copper interconnects to the super via to semi-damascene. And now we are having the BSPDM. And we are going to have more sophisticated interconnects on the wafer backside. As you can see, for the advanced interconnects, we are moving towards the backside interconnects. So regarding to the advanced transistor, the whole industry has put a lot of efforts on this. As you can see, the 3 big companies in this field, the TSMC, Intel, and Samsung, all have their solutions to work towards a manufacturable solution for the CFET. And for the advanced interconnects, still those 3 big guys, the TSMC, Intel, and the Samsung, they all have their own solutions to enable the backside interconnects with different kind of solution, which TSMC has this super power via with the backside contact, and Intel is going to use the power via, and the Samsung proposed a new idea of direct backside contact, or called the DBC. So regarding to the development of the 3D stack transistor, actually there's a long history. I would like to say that the PKU together with the Hong Kong UST was the first to experimentally verify the stack transistor concept back to 2004. And after that, the CICICT from France in 2000 2009, they were the first to demonstrate the 12-inch wafer integration with the two layers of transistors stacked on top of each other. And until 2018, IMEC was the first to propose a really emergent solution to have the stacked transistor as a manufacturable technology kind of solutions. And it takes around like 20 years from the concept to R&D. It really takes a long time. And regarding to the CFACT, actually there are two kind of approach. The first approach is the monolithic CFAT. Basically, you are doing the transistor stacking on a single active area of nanosheet or things. And the benefits of doing this is the two layers of transistor, they are all self-aligned. They are formed in a self-aligned manner. However, the problem of this approach is it requires a lot of high aspect ratio processes. You need to do the epi and the gate formation within a very, very narrow trench, and you are relying on timed edge to realize the separated processes for the N and P stacked on top of each other. So the process development for the monolithic CFET is very challenging. And the other solution is the sequential CFET. It features a much more manufacturing-friendly process. So you basically do a one tier of transistor, then you use wafer bonding or other transferring technology to have another layer of semiconductor on top of the first tier. And then you can do another layer of transistors. The benefits of this one is there are no high aspect ratio processes, and it's very manufacturing friendly. But the cons is you are relying on the photolithography to align the top and bottom transistor. There will be a lot of overlay problems between the top and bottom transistor. So as you can see, the monolithic CFET and the sequential CFET, they all have their benefits, but they all have their own flaws. So we really need to think about, is there any other third solution? And today, I'm going to share with the solution regarding to this. And come back to the backside roadmaps, as we already discussed, the industry is adapting the backside power, which is the backside PDN or BSP. And there's a lot of discussion about how to use the signal on the wafer backside, which comes with the BSS. And the industry is also talking about, can we do something else? And for here, we propose a new idea of doing the transistor on the wafer backside, which we call the backside stacked FET, this work. And then we are also going to think about, can we do different circuit functionality on both sides of wafer, which is called the dual side integration. And by combining these two, looks like there is really a solution to enable one quadrillion transistor in a system. So let's go through this. And regarding to the process flow, before we talk about that, I want to first talk about the scaling roadmap of the advanced technology. So in the old time, or like 20 years ago, the whole industry is relying on the pitch scaling to reduce the contact poly pitch and also the fin pitch to reduce the transistor size to make more transistor packed in a chip. So, however, because of the physics limit is approaching, looks like there's no good way to do this the pitch scaling anymore. Then the industry is thinking about use the DTCO method to do the hyperscaling. And in terms of the hyperscaling, actually, you are relying on reducing the number of fins to, for example, reduce the fin from the 3 to 2 and 2 to 1 to reduce the cell height. And the other way is to do the stack transistor, which is the CFET. So you basically put the N and P's active area on top of each other so that you can further reduce the standard cell height. And it looks like in terms of the hyperscaling, the CFET is the end with a 3T cell height. But is that the real solution? We need to really think about this. So that's why in this work we demonstrate a new idea which can further enable a 2.5T one-fin transistor, which is called the FlipFET. And I will go through the detail in the later on discussions. And the self-aligned FlipFET actually features a very interesting enablement. So for a standard FinFET, as you can see from the left-hand side, you have a PFET and you have an NFET put in a planar way, and they are adjacent to each other on the same plane. So what if you flip the NFET or PFET to the backside of the other transistor, so that you will have a transistor stacked in a back-to-back manner, so that you will have two transistors stacked on top of each other with their half of the footprint of the FinFET or other planar integrated transistors. And then the other thing I want to mention is the interconnects. As you can see, we also have the interconnects of the FinFET split into half, and top half is for the front side of the transistor, and the other half is for the bottom side of the transistor. And I will talk about why this is very important. Thanks to this very packed standard cell design, the FFET actually features a very symmetrical device design. So you can see the NFET and PFET, they are on either side of the wafer, and we have their individual interconnects for them. Yeah. So the overall, the standard cell height is reduced into half. And regarding to the process flow, for here, I just want to go through a very brief view of the process flow. So for example, let's have a FinFET like this. This is a standard FinFET. You have a fin over there. And then what's the next actually is if you do a wafer flipping. You do a wafer flipping, and then you will have the device structure like this. So it's something like you have the bottom side of the transistor now being on the top, which is the substrate. And on top of this, if you do a wafer thinning to fully remove the wafer substrate, and then you do the wafer thinning stop on the STI, then you will have a structure like this. So at this time, you will only have the fin and the STI, okay? And the substrate is fully removed. And on top of this, if you do a selective oxide etch, and to keep the silicon still over there, then you will have the fin being exposed. And now you can see the amazing part is actually here. Previously, for the FinFET, the top part of the fin actually is used for the channel to make a transistor, but the bottom part of the fin is not used. By using this method, you flip the wafer, you remove the wafer substrate, and now you can expose the bottom side of the transistor. And now you can see the bottom part of the fin is now exposed. You can do another layer of transistor. And in the end, you will have the FlipFET. So you can see the key concept of this idea is you have a fin, and you utilize the front side of the fin, and then you use the bottom side of the fin. So because of this, the top transistor and the bottom transistor, actually they are made on top of the same fin, and they are self-aligned. So you don't have any overlay problem because they are formed on the same thing. But the only difference is one is on the top part of the fin and the other one is on the bottom part of the fin. And the other thing, as you can see from the 3D cartoon, I also mentioned this before, that the bottom transistor and bottom transistor, they all have their individual interconnects, which is also symmetrical. And I will cover why this is important in the later on discussions. And as you can see previously, the FlipFET actually, their process for the front side transistor and back side transistor, they are done separately. So that will give you a key benefit, which is the aspect ratio. So you can see that because the process of the front side and back side are independent, you can just do the transistor formation in a standard way, like what we have for the FinFET. Because of this, you can actually get a much smaller aspect ratio, which is also the key highlights of the FinFET. Because of the aspect ratio is low, the manufacturability is much higher. So for here, I'll compare the FFET versus the standard monolithic CFET. Because of the separated process from the front side and back side, the FlipFET actually features a much lower aspect ratio compared with the CFET, which is the key process benefits of the FFET. And now we talked about the process of the FlipFET and also the concept. People may ask, looks like this is all on paper. Do you really have silicon? Yeah, yes, we have some collaboration with some of our partners, and actually we get it done. So for here, I show the process flow we have, and you can see this is just a standard FinFET. You have the fin over there, and you have their interconnects stacked on top of the fin. This is just all standard method. And then what would you do the next? Actually, is you bond the wafer to a carrier wafer, and then you flip the wafer. And for here shows the results of the after the wafer flipping, we do the substrate thinning, and this is the result of a partial substrate thinning. You will have around like 40 to 50 nanometer of silicon over there. And this is just because this is just a partial thin silicon thinning down. The next step is to fully remove the substrate, and the substrate thinning is stopped on top of the STI. And now you can see the results. You can have the substrate fully removed. You just leave the fin over there, and you can see, yeah. And the next step is, as you can see here, you have the silicon and you have silicon oxide. And what you can do the next is to do a selective etch. And people may also ask question about, your fin looks so ugly because the bottom part of the fin is reverse tapered, right? And this may not be good for the device performance. And I agree with this. So actually you can do some fin profile improvement. As you can see from this TM image, the fin profile gets a little bit improved. And the next step is to selectively remove the silicon oxide to have the silicon bottom part of the silicon fin exposed. And this is the results. You can see after the STI recess, you have the bottom part of the fin exposed. And what can you do the next? And you can do another layer of transistor on top of this. So for here, I show the results of the backside transistor formation, which is the cross-section of the gate region. You have the cross-section of the gates of the bottom and top transistors. And for here, I also want to mention one critical benefits of the FlipFET because of the split gate. The split gate actually is a very important technology enablement element for the standard CMOS. And this split gate concept is very important for sequential logic, and I will talk about this in detail later. And actually, you can do further fin smoothing process, as you can see from here. Now the fin looks more straight, and the profile looks more beautiful. This is just an optional process of further doing the fin smoothing. And eventually, the result you would get is something like this. You have a bottom gate, and you have a top gate, and you have their corresponding transistor formed in this way. Yeah. And as you can see, the FlipFET actually is a combination of benefits from multiple technologies. And let's get a summarization over here. So actually, the FlipFET combines the benefits of the self-aligned active from the monolithic CFET. It also have the benefits of the low aspect ratio from the sequential CFET. We also features the dual side interconnects, which is from the backside signal. And we also have the backside stacked active, which is from the backside stacked transistors. So you can see all of the benefits from the monolithic CFET, sequential CFET, backside signal, and backside stack FET. All their benefits are combined in the flip FET. So you can see this is really something interesting, combine all the benefits. And now people will ask me another question. Now you have the transistor concept being proposed, and you have their some of the preliminary structure being demonstrated. How about the design of this transistor or transistor 3D integration technology? So now let's go through this. So for here I show the cross section and the cartoon of the 3T FFET inverter. So you can see from here the FFET features two unique features. Basically, because of the two process of the MFET and PFET from the wafer front side and back side are done independently. So you would need to connect them as you will for the CMOS. For example, if you want to do an inverter, you would need to connect the gate of the front side and back side together. And you would also need to merge or connect the drain part of the top and bottom transistor. So in that case, you will need to drill a via to connect the gates and also the drain to form an inverter. The unique part of this is the via is all done by your lithography process or by your layout design. So if you want them to be separated, you can separate them. If you want them to be connected, you just draw a via and get the via being drilled, and you will have them connected. So the drain merge and the gate merge is the via I mentioned here. So this is very critical. And for here shows the layout design for our flip FET on the right hand side layout. Because the transistors are done separately from the wafer front side and back side, so you would need two sets of the layout. One is the layout for the wafer front side, and the other is the set of layout for the wafer back side. And I will talk about the reason why we are doing this. And I also want to mention that, as you can see from the pins over here, you have the VDD, VSS, and also V-in, V-out. But the V-out here, actually, you have the V-out from the wafer front side and the wafer back side. And this is very important for the dual-side interconnect. I will discuss this one in detail later. And now, since we have this 2.5T FFET, let's make a comparison with the 3T CFET. Because the FFET features the power and the interconnect on both sides of the wafer. Now, there would be a very interesting part is actually the FFET features a smaller cell height, which is only 2.5T. CFET actually is 3T. But the CFET actually, for their design, their signals are all being placed on the wafer front side, and also power are placed on the wafer back side. This would result in, for example, you have 3T layout design. You only have 3 signals on the wafer front side, and you don't have any signal on the wafer back side. But for the 2.5T FFET, because you have a 2 layer of interconnect, one is the front side and the other one is the back side, you would have 1, 2, 3, 4. You have 4 signals over there. So this results in a much higher number of pins or much higher numbers of signals enabling a smaller cell height. And this is actually very important. You get 4 signals within a smaller area by using the flip FET compared with the CFET. This would open a totally new regime for the cell layout design, and I will talk about this one in detail later. And now, as I mentioned before, the split gate actually is critical for the standard CMOS technology. The reason behind this actually is the sequential logic. And I will, for here, show the clocked CMOS structure, the layout, and also the circuits diagram. You can see for the clocked CMOS, you have an inverter in the middle, and the input signal for this inverter actually is complementary. You would have a clock being injected into the gate of the PFET, and you have the clock bar being injected or being connected to the gate of the FET. So you can see for this inverter, the two signals are being placed on the FET and PFET, and they are separate. To enable this, you would need the gate of this inverter for the FET and PFET being separated. And this is very important because this is a very critical element for the sequential logic. And by doing this, if you have a split gate enablement, you would not waste any area. But if you want to use a CFET, which is common gated, if you want to do that for the CFET, you would waste area. So this is a critical element for the FET. And for now, as far as we know, the FET is the only technology which can enable split gate structure for the stack transistor technology. For all of the other transistor stacking technology, such as the monolithic CFET, you don't have any manufacturable solution for this. And based on this concept, we designed a very important sequential logic gate, which is the D flip-flop. So for here, as I mentioned before, because the transistor, the layout, actually there are two sets of it. One is from the front side and one is the back side. So you would have something like this, and this is very important. As I mentioned before, if you have a CFET, you would waste area. So you can see from here, the CFET features a much wider layout, which is 10 CPP, but for FET, we only need 7 CPP. And the other thing is people are thinking about, can we really do split gate for CFET? Actually, you can do that, but the process is very complicated and you would need to waste area for this. And you can have a 3.5T split gate CFET, and by doing this, the cell height is much larger. So because of this, actually we have designed around 30 standard cells for CFET and FET. And you can see FET features the smallest cell area, and also because of the sequential benefits, you get special benefits of the sequential logic of the 2.5T FET compared with the common gate CFET. And this is very important. And people will ask me another question, since you have designed all the layout and you have the transistor architecture or concept, how about the performance? And actually, we also did the performance analysis, as you can see from here. Well, here I shows the power versus the frequency plot for the CFET, FlipFET, and also the FinFET. You can see actually the FlipFET shows the highest frequency at the same power. And the reason behind this is the FET is the smallest. And because of the smallest standard cell height, you would have smaller back-end of line loads. And this is the reason why FET is better than the FinFET. And compared with the CFET, there are two benefits beneath it. One is the cell is smaller. You would have smaller back-end of line loads, and also within the cell, actually, the FET features a much lower parasitics compared with the CFET, as you can see from the partition on the bottom right corner. And the people will also ask me another question. It looks like you did all of the transistor stacking on the fin structure, but the fin is something already needs to be replaced by the GAA. Can you do the stacked GAA using the flip stack concept? And the answer is yes. You can do the nanosheet stacking by using the flip stack concept. So that's why I mentioned here, the FlipFET actually is an integration method. It's independent on transistor architecture. You can do fin stacking, you can do nanosheet stacking, and you can think about any other structures. As long as you are doing the wafer flipping and do the two processes independently, you would have all kinds of structure being enabled by this FlipFET concept. And we also studied the performance of the FlipFET based on the nanosheet structure. As you can see, because of the independent routing and also the the nanosheet design, actually for the FlipFET, to enable the GA structure or nanosheet structure, you can have a much wider active area or larger active area, so that you will have a better performance. So that's why on the right hand side picture, by using the FlipFET concept, the power performance actually is better than the CFET. Yeah. So now looks like we have the standard cell and we also have the device performance. People ask me another question: can you do a chip? Can you design a chip? And that's also very important. So now let's go through this. And before discussing about that, I want to propose and discuss with you guys about the dual-side interconnects. For here shows a circuit diagram of the inverter. You have a in and you have an out, and in a standard planar integrated transistor technology, all of the input and output signal are being placed on the wafer front side. And the output pins are the drain of the MFET and PFET. But for the FFET, since you have two layers of transistor and you have two layers of interconnects on both wafer front side and wafer back side, this will enable a totally different cell design concept or cell interconnect concept. Because we have the output pin being placed on the wafer front side and wafer back side, and now the layout, the circuit diagram would be a little bit different, because you can have the output pin placed on the wafer front side and the wafer back side, and those two output are being connected by the drain merge, as you can see from the right hand side pictures. And this would enable a totally different concept of the interconnect. Let's check this. So for here I shows a concept demo of an inverter being used as the first stage of transistor gates, and is driven the inverter and the NAND on the second stage. And because we have the input signal and the output signal on both sides of the wafer, and in this case, the output pins actually can be on either side of the wafer. And in this case, you can connect the front side output pin to the input pins of the inverter on the wafer front side. And for the wafer backside, actually, you can put the outside backside output pins connected to the input pins of the NAND on the wafer backside. And by doing this, you can actually have the routing being placed on both wafer front side and wafer backside. This is just a demonstration of how can we do dual-side interconnects. And actually, we did the place and the routing on based on this concept with some collaboration with Professor Lin's group from Peking University. So for here shows the design rule violations of the CFET and the FlipFET versus the block area. And you can see actually the split gate FFET actually, or the FFET features the smallest number of design rule violations because of this dual-side routing innovations. And the reason behind this is, if you think about this, for the CFET, you have 3 pins all placed on the wafer backside. But for FFET, you have 2 pins on wafer front side, and you have 2 pins on the wafer backside. So in that case, if you really think about this, the input pins actually of the FFET is much lower in terms of the pin densities compared to the CFET. And because of the lower pin density, the routing congestions would be much lower. And because of this, so that's why the FFET shows the least number of design rule violations. And now, let me show you the results. Actually, you have the PNR result, you have the this is the PNR routing result of the CFET, and also the 3.5T split gate CFET, and our 2.5T FFET. As I mentioned before, the FAT features two layers of interconnect, which is on wafer front side and wafer back side. So that's why you can see there are two routing layout from the wafer front side and wafer back side. And the FAT features the smallest layout area based on the RISC-V core we have designed. And now it looks like we have already going through all of the logic technology, and previously the industry is using the planar transistor, and the planar transistor 3D features the 2D channels, and their placement are 2D integration. And 15 years ago, people proposed the FinFET, and we have the FinFET being being in volume manufacturing for last 15 years. The FinFET features 3D channel, but the integration of the transistor is still 2D integration. And then we are going to have the GA transistor, and the difference is the GA features 3D channel stacking. You have 3 layers of even 4 layers of nanosheets being stacked, but the transistor integration is still 2D. And on top of this, people are proposing to using the BSPDN, and the BSPDN features another level of 3D, which is basically you have 2 layers of interconnects, and this is a 3D interconnects concept. And now, what can we do the next in terms of the 3D? And actually is the FAT. The FAT features the 3D channel because we are using either the thin or 3D GA structure. The channel is 3D. And also the placement of the MFAT and PFAT actually is also 3D. They are being placed in a vertical way. And if you think about the interconnects, it's also 3D. So you can see the FAT actually is very unique. It features 3D. 3D channel, 3D integration, and also 3D interconnects. So that's why we think FAT is the ultimate form of transistor technology in terms of the CMOS scaling. It combines all the benefits of the 3D integrations. And now let's move to another regime of the system integration. We have already covered all the concepts of the 3D integration in terms of the advanced logic. How about something else, which is the advanced packaging? So in terms of the advanced packaging, starting from the beginning, we're using the 2D integration. You have 2 chips being placed on a PCB board, and then people are using the silicon interposer to have the 2.5D integration. You have 2 chip or even more chip being placed on our silicon interposer, and so that you can put them closer to have a much higher bandwidth. And then people are starting to think about the 3D packaging, which uses the TSV or hybrid bonding to have several layers of chips being placed on top of each other. And the people are also thinking about, can we do monolithic 3D stacking? So basically you have a wafer, and you can do layer transferring, and then you can do another layer of a transistor or another layer of circuit functionalities such as the memory or sensing. And by doing this way, you can do multiple layers of circuit on top of each other. So this is the 3D monolithic stacking. But is that the end? Is there anything else? Yes, there's something else. So now let's take a look at the FlipFET or the flip integration. Because as I mentioned before, the wafer front side and wafer back side integration, actually they are independent, which in the other words telling us that you can do actually a logic from the wafer front side, and you can do the memory on the wafer back side. And in the other words, you can do 3D dual size functionalities. This is a very important concept. And now the integration of the circuit functionality is no longer on the wafer front side. You can do two sides. You can do the integration on 2 sides of the wafer. And the other thing I want to mention is actually because you have two layers of circuit functionalities, you can have the bumping on each side of the wafer. And in other words, you can do the 3D dual-side bumping and hybrid bonding. And this is very important. For the hybrid bonding we are having now, actually, they are doing the standard way is to do the wafer face-to-face or chip face-to-face hybrid bonding. You cannot do the hybrid bonding of the chip by doing in a way like face-to-back and back-to-back bonding. But if you have two sides of bumping, actually you can do a much wider bonding regime, which is you can do face-to-face bonding, back-to-back bonding, back-to-face bonding. So there are multiple ways you can do the bonding, which is totally new. And to enable this, for here I show an example. You can have the you can start with a wafer like this, and then you bond another wafer, and then you flip the wafer, remove the substrate, and you can have another set of circuit functionality on top of it, and you can have the bumping on the wafer backside. And take a look at the 3D cartoon of the cartoon here. Actually, you have the bumping on each side of these two sides functionality circuits, and you can do multiple stacking of this. And this turns out to be, which is what we call the flip 3D integration. The wafer stacking or the chip stacking is no longer on one side of the wafer. Now you can do the stacking of the transistor on both wafer front side and also the wafer back side. This would open a totally new regime of the chip stacking. You can have more circuit functionalities on top of this. And now, since we have already discussed about the advanced packaging and also the advanced logic, do we have the solution for one quadrillion transistor? I believe we have. And now it's the time to merge the two methods or two rows. So what we think for the flip 3D integration is by combining the flip FET together with the 3D IC, you would actually have the dual side 3D. Basically, you have wafer front side and wafer back side to have two kinds of circuit functionalities. And further go through, you would have the hybrid bonding on each side of the wafer, which enables the face-to-face, back-to-back, back-to-face hybrid bonding, and which is what we call the flip 3D integration. This is enable the 3D dual-side integration, 3D dual-side hybrid bonding, and 3D dual-side chip stacking. And this would open a totally new regime of chip stacking and the transistor stacking. And now let's move to the conclusion. I want to take the city building as example, like as an example for the involvement for the integrated circuits. For example, like 1,000 or 10,000 years ago, when we were still in the Stone Age, we built a small tent like this. This is just like the beginning of the transistor technology. We have the bipolar junction transistor, and every component of the circuit is a discrete component. But this is the beginning. And after that, we have the, for example, the 1 micron technology. It's just like the city we have like 200 years ago, or like 400 years ago, like the ancient city in Ming Dynasty of the Beijing. You would have everything planar, and every houses over there is just one floor. It's very flat, and the density of this city is very low. And then we have the 3 nanometer as we have now. It's just like a modern city, like the Beijing we have now, and you have the ring roads, the 5 ring, the 6 ring, or even the 7 ring, right? You have all kinds of the skyscrapers in the city. You can put more people, and the city is huge. It's just like the VLSI we are having now. How about the future? Because there are more people. We are using what? We are using the subway. We are using the subway to communicate the people, so that you would. It's just like the BSPDN to have another layer of interconnect on the city bottom, so that you would have a enhanced interconnect. But is that the end? No. You would have the dual side transistor, which is called the underground city. So like the Beijing we have now, you have the city on the front side of the ground, on top of the ground. But what if you can build another city on the bottom, on beneath the ground? So you have underground city. It's just like the dual side transistors. And then, how about the F3D? And I would say this is just like the vertical cities. You can have the cities like with multiple layers of functions. You have like the residence area, you have the industry area, and you have the merchant area. It's just like a vertical city. This is the ultimate form of the transistor, or ultimate form as the city building with the enhanced computation power. So we think F3D is the ultimate form for the transistor or the technology development. So now let's make a conclusion. So in this discussion, we have discussed about the FlipFET, which is a breakthrough technology for the transistor stacking, which features a very new concepts of circuit design and also the transistor design. It combines the benefits of the TFET, the backside signal, and the backside stack FET. And you have a fully functional backside wafer backside. You don't have it, so for now you have the transistor and you have the interconnect. So that's why we call it fully functional backside contact. And because of the self-aligned feature, the process of the FlipFET is actually much easier compared with the monolithic CFET. And the other thing I want to mention is the interconnects. You have the wafer front side and you have the wafer backside. So this would open a totally regime for the transistor stacking and also the transistor interconnecting. And we also discussed about the F3D. This is a new paradigm uniting the advanced logic and packaging. You would have the dual side functions and also the dual side bumping with vertical integrations. And we believe F3D is the ultimate form for future's chip technology. That's pretty much what we have for today. And thank you very much for your attention. Thank you very much.